Hello, this is the last lecture on normalization. We're going to talk about 3NF decomposition. Okay, so 3NF, or third normal form, it is useful because sometimes BCNF does not guarantee that it's going to be a dependence-preserving decomposition. Okay, so it is efficient for checking for these violations. On updates these are more important. So we need to define a weaker form. BCNF is pretty hard to achieve, and it also doesn't guarantee that it's going to be dependency preserving. Okay, so because of that, we sometimes choose to use a weaker form, which we call 3NF, third normal form. So this one does allow some redundancy, okay, but it is going to be guaranteeing that it is going to be dependency preserving and it's going to be also lossless, okay, which is so how do we know if something is in 3NF? So with BCNF, each of the functional dependencies have to be at least true for one of these. So it has to be true for one or two. But with 3NF, we have a third option. So if these two are not true, but if this is true, it's still going to be in 3NF. It's not BCNF. Okay, so for each of these dependencies, it has to be trivial, which, you should know by now. This is rarely the case, where the right-hand side is a subset of the left-hand side, okay, or left-hand side is a superkey. Okay, so superkey meaning with the left-hand side, we are able to get the whole relation R. If that's not true, then we look at the third one. So each attribute on beta minus, so the right-hand side minus the left-hand side is part of a candidate key. So we call this prime. Okay, so I know that doesn't make a whole lot of sense, so we'll look at an example and it'll be easier to understand. Okay, so whenever we do this 3NF, it's going to be both. It's guaranteed that this decomposition is going to be lossless as well as dependency preserving. 3NF is weaker than BCNF, and let's look at some comparison between the two. So there is a compromise with 3NF. Not all redundancy is removed. You will sometimes see some redundant ones. Okay, but dependency preserving is always possible. It's always guaranteed, unlike BCNF. Okay, so 3NF decomposition is based on the concept of minimal cover of set of function dependencies. This was covered in our last lecture when we talked about the canonical cover where we get rid of redundancies. So here we have an example. The relation is called department advisor. We have three attributes. We have a student ID, instructor ID, and the department ID. We have two functional dependencies. The first one says, if you know the student's ID and the department they belong to, there's only one instructor that's going to be advising. If we know the instructor's ID, there's only the one department that they belong to. Okay, so these are going to be our two functional dependencies. So we have to think about what the keys are in this case. So here, if you know the student ID and department name, you can also get the IID, the instructor ID, which is the whole relation, right? So this is one candidate key. Sometimes there's more than one key. With instructor ID, we can get instructor ID. That's trivial. We can also get department name. So student ID it's not part of it, right? So we have to add that as part of the candidate key. So if you know the IID and SID, you can get the whole relation. So this is another candidate key. So let's see if this is in 3NF. Let's take a look at the first dependency. Okay, so is IID part of the left-hand side? No, it's not true. This one also, department name is not part of the left-hand side, so it's not trivial. Okay, is the left-hand side a super key? So we have SID and department name on this one, which we know is a key. It's a candidate key. So this one is fine. This one does not violate the rule for 3NF. Let's go to the next one. We have IID and department name. Is IID alone enough to get the whole relation? No, right? Because with this, I can get IID and department name, but I cannot get SID. So this is not a key. So with the 3NF, there was a third condition, right? Where each attribute A on the right-hand side is contained, it's part of a candidate key. So the right-hand side, which is department name, this has to be a prime. Prime meaning it has to be part of a candidate key. So we have two here. So let's take a look at the first one. Is department name part of this candidate key? Yes, it is because we have department name here. Okay, so department name is a part of, it's contained in a candidate key. So we would say department name is a prime because it's part of a candidate key. So because of that, this is also in 3NF. If we were trying to figure out if this was in BCNF, then it will break the law because this is not a prime and this is not a super key. But because we're trying to figure out if it's 3NF, we have that third condition and department name is a prime because it's part of this. So we don't have to decompose this further. We know that this is already in 3NF. Okay, so we need to check all the functional dependencies in FD. This one had 2. If there were 10 functional dependencies in FD, then you do have to check all 10. Okay, and then the next thing you check is, so for each functional dependency, you have to check if it's a prime, which is rarely the case. So then you have to check if the left-hand side is a key, a super key. And you do this using a closure. So you would do alpha, and you would have the closure sign, which is the plus sign, and see what you can get. So with the left-hand side, if you're able to get the whole relation R, we know that this is a super key. Okay, if that's not true, then you go to the third option and we see if the right-hand side, which is beta, is part of a candidate key. Okay, so we call that a prime. Okay, so let's go into how we can do this. Here we have a schema called customer banker branch, which has customer ID, employee ID, branch name, and type. The key here is customer ID and employee ID. So we have some functional dependencies here. If you know the customer ID and the employee ID, you know branch name and type. If you know employee ID, you know branch name. If you know the customer's ID and branch name, there's only one employee that deals with it. So these are going to be our 3 functional dependencies. Okay, so we want to compute the canonical cover. This is how you would decompose something, right? So we talked about getting rid of extraneous attributes. Okay, sometimes the whole functional dependency is extraneous because we're able to infer it using other ones. So here, branch name is extraneous on the right-hand side of the first dependency. So branch name here. Okay, why is that? Because if you using this one, if you know the employee ID, you already know the branch name, right? So you don't need customer ID. That's actually making it weaker. This is stronger, right? Just by looking at the employee ID, we can get branch name. So this one is extraneous because of this condition. So we can get rid of branch name here and just we are left with customer ID and employee ID gives you just type. Okay, this one is fine because we're not able to infer this using other ones. And this one also, same. Okay, so no other attributes are extraneous. So this is going to be our canonical cover. We were able to get rid of one attribute, which was branch name on the first one. Okay, so the next step is each of these functional dependencies, each attribute from each of these dependencies become a relation. So this is our original relation. So the first one's going to be R1. So R1 contains customer ID, employee ID, and type. R2 contains employee ID and branch name. Okay, and then R3 contains customer ID, branch name, and employee ID. Okay, so we were able to come up with these 3. Okay, so sometimes you will see that one of these is a subset of another. So here we have employee ID and branch name, and here we have employee ID and branch name and customer ID. So this is redundant, right? This is redundant, so we can get rid of the second one here, and we are left with the first and the third. Okay, so this is not it. So we're not done yet. If none of these contain the key, then we have to add a third one here, which contains the key. Okay, but in this case, it does contain the key. So this is going to be our final 3NF. Okay, customer ID and employee ID type is 1, and the second set is customer ID, branch name, and employee ID. This is how you decompose something into 3NF. Okay, so it's always possible to decompose a relation into 3NF that it's going to be always guaranteed that it's lossless as well as dependency preserving. Okay, with 3NF, it's always going to be lossless just like 3NF, but dependency preservation is not always guaranteed. It's not always possible. Okay, so these are some differences between 3NF and BCNF. In 3NF, there should be no transitive dependency that is not non-prime attribute should be transitively dependent on the candidate key. So in BCNF, for any relation, A determines B, A should be a superkey of the relation. This is talking about how the right-hand side can be a prime and it's still going to be in 3NF. So this was a third condition of determining if something is in 3NF. So we all know that BCNF is harder to achieve than 3NF. So 3NF is less strong. This is stronger than 3NF. But redundancy is high in 3NF. Here it is a lot lower in BCNF, pretty much non-existent. But this one, sometimes there's going to be redundancy in 3NF. So dependency preservation is guaranteed in 3NF, but not in BCNF. BCNF is difficult to achieve because there are only two conditions that makes it BCNF. Because we have the third condition, this is easier than BCNF to achieve. So our design goal, ideally, we want it to be in BCNF. We want it to be lossless as well as dependency preserving. If this is not possible, meaning it's BCNF, it is lossless, but this was not preserved, then we want to go to a weaker form, which is in 3NF. But if you go with this route, there's going to be some redundancies because it is 3NF. So we talked about how we can decompose something into 3NF. We first compute the canonical cover by getting rid of all of the extraneous attributes and extraneous dependencies, and each of those resulting dependency in FC will become a relation. If something is a subset of another set, we get rid of those. If the key is not part of it, you have to add another set which contains the key. So just to kind of jog your memory on how to get your minimal cover, or we also call it canonical cover, we want to have only a single attribute on the right hand side. So if you have more than one attribute on the right hand side, you want to kind of put them apart and have multiples. After that, you want to eliminate all of the unnecessary attributes or redundant or extraneous attributes from the left hand side. Okay, we want to also delete all the unnecessary functional dependencies. So these are dependencies that can be inferred using from other dependencies. So after you get rid of all of those, you will get your FC, which is your functional canonical cover of your functional dependence. Here is an example. I have copy pasted over kind of the steps to take to get your FC. So this is our original relation, which contains A, B, C, D, E, F, G, H. And then we have these dependencies. First step is to make sure that the right-hand side only contains a single attribute. So this contains 1. This also contains 1. This one contains 2. So I would pull these apart and say EF determines G and EF determines H, which I have here. And you do the same thing for this one because there's E and G. I pull them apart to be different. One has E and one has G. Okay, so we want to minimize if there's any extraneous attributes on the left-hand side. Okay, so for this one, we have A, B, C, D determines E, right? So let's see if B is extraneous. So looking at this one, if I know A, I know B, right? So because I have A here, I already know B. So actually this is not necessary. This is extraneous. So I'm going to get rid of this B here from this particular dependency. Okay, let's see if we can get rid of some dependencies. So we're going to always kind of go with the bigger ones here. We have A, C, D, F determines E. A, C, D, F determines G. Let's take a look at this one first. Can we remove this? Are we able to infer this using something else? Maybe. So from this tab, we got this one, right? So we can add the same attribute on both sides. So we're going to add F onto the left side and the right hand side. Okay, so we added F here and we got A, C, D, F, and then I added F to this one, so we have E, F. Okay? So this is true, right? And then we have E, F determines G. So if I combine these two and using transitivity, I can infer that A, C, D, F determines G. Okay, which we already have in here. We were able to infer this using two other dependencies, right? So we can infer it using these two. So this is not really necessary. It is redundant. So we're going to get rid of this whole thing. Okay, similarly, we can get rid of this one as well. So using this, we are able to add F on both sides. So this is what we got. And using this, and then using this, we are able to infer that A, C, D, F determines E. Okay, so because of that, we can remove this as well. Okay, so the final result is going to be A determines B, A, C, D determines E, and then these can be put back together and we call it EF determines GH, which is what we have here. So this is going to be our relations. We have AB, ACDE, and then EFGH. Okay, are we done? No. We want to first check if any of these is a subset of another set. So AB, is AB contained in this one? No. This one? No. So there's no redundancy, so we can keep everything as is. Okay, and the very last step is make sure that a super key has to be contained in one of these sets. The super key here is ACDF because with ACDF, I can get the whole relation R. Okay, so you have to kind of practice how to compute a candidate key. So is ACDF part of any of these? Not here. This is missing the F. This one, no. So because of that, we do have to add this as a fourth relation. So now this is our final result. The new relations, we have AB, ACDE, EFGH, and then we have lastly ACDF. Let's go over another example here. We have relation R, which contains CSJD, PQV, and we have 1, 2, 3, 4 dependencies. This is kind of a little bit annoying because we have so many on the right hand side. So we have to take these apart and say C determines C is trivial, so we're not even going to write that. C determines S, C determines J, C determines D, and so on. And then we have these three here. Okay, so let's try to remove some of these redundant function dependencies. Okay, are we able to remove C determines S? We'll see. So using C determines J, right? And then we have J determines S here. By transitivity, we can infer C determines S. So this is already inferred by using these two, so I can simply remove this one. What about C determines P? Let's see. So I have C determines S, which we had inferred using these two. I also had C determines D, so I can get C determines SD by combining it. And so by transitivity, using this one and then SD determines P, I can infer, say, C determines P. Okay, so we do not have to have this because we're able to infer using other dependencies. So I can remove this as well. The rest are fine, so we are left with C determines J, C determines D, C determines Q, V, and then we have these. Okay, are we able to combine some of the right-hand side? So we have C here, C, C, C. So these four can be combined back into C determines J, D, Q, V. And then we have these three. So these are our four relations. Are we done? Do any of these contain the key? Yes. C, J, D, Q, V. This does give you the whole relation. It is part of this relation, so we don't have to add it as a fourth one, or the fifth one, I mean. So this is going to be our final set. We have these four new relations. This is our original, and then we have decomposed this into 3 and F into these four. Okay, so given that, let's try these two exercises. You will see something very similar, just like this one, on the final exam. So it is great practice. The first step is to identify all the candidate keys. Okay, and the next step is we want to see if this is in 3NF or BCNF. It might be both or just one. Okay, if it's not in BCNF, decompose it into BCNF. If it's not in BCNF or 3NF, decompose it into 3NF. So it has 4 parts, so this will take you some time. Okay, so I have copy pasted over the conditions of 3NF and BCNF. Okay, so take a few minutes to work on this, and once you're done, hit play. So what are our candidate keys? So let's see. So with B, I can get B, that's trivial. Using this one, I can also get C, so I added C to the closure of B. If I know C, I can get D and A. So that's the whole relation, right? A, B, C, D. So B is a key. There's nothing else that can be a key. You can try taking a closure of C or A or anything, but with C, I can get C, D, A, but there's no way I can get B with C. So B is our only candidate key possible. Okay, number 2, we want to see if this is in 3NF. Let's check the first one, which we had these conditions. Okay, so C determines D. So we know that it is not trivial. Okay, and C is not a key. Okay, is D part of a candidate key? Is D a prime? Also no. Okay, so this causes a violation. Same thing with this one. This is not a key. A is not part of prime. A is not a prime because it's not part of the candidate key. Candidate key is B. Okay, and this one, this is fine because B is a candidate key. So these two violate the rule for 3NF. Okay, let's see if this is in BCNF. Okay, is it in BCNF? Let me see. So this one still breaks the law. This one breaks the law. This one's fine. So this is both not BCNF or 3NF. So that means we have to decompose this into 3NF or BCNF, and let's go over how to do each one. So let's first go over the BCNF route. Okay, so these were the two that were causing a violation for BCNF. So you can start with either one. Depending on what you start with, you might get a different result. But I always just go with the very first one that you see in this order. So let's take this one and then remember the formula. R1 is going to be left and right. R2 is going to be relation R, which is A, B, C, D, and then subtract whatever is on the right hand side. Okay, so since we have C and D, R1 is going to contain C and D, or R2, and then R1 is going to contain our original R, and then we're going to subtract the right hand side, which we have D. So after this is gone, we are left with A, B, C. Okay, so let's see if this is still in BCNF. So CD, we can use C determines D. So this one does not cause a violation. With this one causes a violation. We can use either one. So C determines A. Okay, with C, is C a key for R1? No, because with C, I can only get A and C, not B. Well, this one still causes a violation, so I'm going to decompose R1 further using this one. So we're going to apply this same thing to this formula here. Left and right, which is C and A. So I have that here. And then R2 is relation R minus the right-hand side. So R1 has A, B, C. Right-hand side has A. So if I get rid of the A here, I am left with B and C. Okay, and these are now in B, C, and F because I can apply this. And C is a candidate key for R12 because we have C and A. And this one, I can use this one. With B, I can get C, which is the whole relation. So every one of these now are in B, C, and F. So we have decomposed this to three C and D, B and C, and C and A. Yeah, we can also check, since dependency preservation is not a guarantee, we can check those as well. So this one was preserved in this R2, C determines A was preserved in R12, B determines C was preserved in 11, so this was apparently, it was dependency preserved. So question number 4 was decompose R into a set of 3 and F relations. Okay, we are able to compute the canonical cover. There was nothing redundant, and we were able to combine this into C determines DA. Okay, so we know that this becomes 1, this becomes 1. So C determines DA, B determines C. Okay, is the key part of this. We know that B is a key, and B is part of R2, so we do not have to add a third one. So this is going to be our 3NF decomposition. We have this and this. Our last exercise, very similar. We wanted to see if this is in 3NF. If it's not, decompose it. And in order for you to do this, you do have to find out what the candidate keys are. This might take some time. And then we have, is it a BCNF? Why not? And if it's not, decompose it. And after you have decomposed it, also determine if this is dependency preserving or not. So this will also take a few minutes, and once you're done, hit play. Alright, so let's first figure out the candidate keys, and we have a lot actually in this case, so just do your best to come up with every single possible candidate keys. On the exam, I think I will just indicate exactly how many keys exist, so that way you know if you're, if you get it or not. So just using the closure, I will probably start with AB. With AB, what can I get? With AB, I can get AB and C and D, which is R. So AB is a very easy one, right? So AB is a key, and you would just, try different combinations. If you do CD, with C, I can get A and C. With D, I can get D and B. So we have all A, B, C, D. CD is a key. CB. So if I know C, I can get A and C. Okay, and if I know A and B, I can get C and D. So CD is another possible candidate key as well as AD. So in this case, we have 4 candidate keys. Okay, so based on this, let's see if this is in BCNF. Okay, so let's see. So looking at the first one, we do have to check each one. This one, does this break the law? Well, AB is a key, so it doesn't. This one's fine. This is also fine because AB is part of a candidate key, or it is a candidate key, so these are fine. What about this one? Is C a key? No. Is A prime, meaning is A part of a candidate key? It is, as A actually appears here and here, so A is a prime. So this is in 3NF. What about this one? B is not a key. Is B a prime? Yes, because B appears here and here in these two candidate keys. This is a prime, so actually this is in 3NF, meaning we do not have to decompose. Okay, number 2 is this in BCNF? Let's similarly, so these two are fine because these two are candidate keys. With BCNF, we don't have that third condition where the right-hand side can be a prime and it's fine. So because C is not a candidate key, D is also not a candidate key. These two break the rule. Okay? So I'm going to start with the very first one that appears in this order, but you could start with this one also. But I'm going to start with this one for this example. But using this one, I am able to decompose it, right? So we apply that to this one. We have a left-hand side and right-hand side, which should contain A and B. And the R2 should be R minus the right-hand side, which is A. So if we get rid of A, we are left with B, C, D. So we have R1 and R2 here. This one is in BCNF because in this relation, C is a candidate key for R1. With this one, we can use D determines B. Is D a candidate key for R2? No, because with D, I can get D and B, but I cannot get C. Okay? So because of that, this still breaks the rule for BCNF, and I'm gonna use this one to decompose R2 further. So I'm gonna I'm gonna plug these in to this formula. Left and right gives you D and B. R2 is gonna be BCD minus the right-hand side, which is B. So if you get rid of this, we are left with C and D. Okay, this one's fine because D determines B. B is a candidate key for R3. This one's fine because we are only left with the trivial ones, such as C determines C. D difference D. Okay, so this is a BCNF. So we have taken this original R and we have decomposed it into CA, BD, and CD. Let's check if this is dependency preserving or not. Okay, so here AB determines C. Do we see ABC anywhere in here? No, this one doesn't have B. So yeah, this was lost. Same thing with this one. ABD cannot be found in any of these relations. What about CA? It appears in R1, so this was preserved. We have BD here, which was preserved in R2, but because we have lost these two, it is not a dependency preserving. So what happens if we had started with the other one? So these two were the ones that were breaking the law, right? So what happens if we start with this one? Let's see. So we have D determines B. We plug this in, we get BD on one side, and then we have the R, right hand side is B, so we get ACD. This one doesn't break the rule because D is the key for R1. For this one, I can use C determines A. With C, I can only get A and C. I cannot get D. So this one still breaks the rule, so I'm going to use this one to break this down further. I'm going to plug this in, and I have left and right side, which has A and C. And R2 is going to be relation R minus the right-hand side. I have relation R2. I'm going to get rid of A, and I'm left with C and D. Okay, so we have BD, AC, and CD. BD, AC, and CD. So in this case, it didn't matter which one you start with, we still got the same results. So because of that, we have lost these, and it is not dependency preserving.